Welcome to the Unit 1 EOC review. Unit 1 in EOC review is on the relationship between quantities and expressions. So we're going to talk a little bit about the types of numbers that we can have when we're talking about those numbers, and we have rational versus irrational numbers. So just some reminders: a rational number is a whole number. A fraction, it's a repeating decimal or a decimal, a decimal that terminates. It can also be a perfect square root or perfect cube root. It's any number that can be written as a fraction. And then our irrational numbers are things that are non-terminating or non-repeating decimals, non-perfect squares, and the number pi would also be an example of an irrational. So like the number square root of 25, that's a perfect square, that would be rational, but the square root of 26 is not a perfect square, so it would be an irrational number. A couple of reminders: the sum of an irrational and a rational number is always irrational. So if you add, that's what sum means. If you add an irrational number to a rational number, you're going to get an irrational answer. The product, so if we multiply a non-zero rational and an irrational number, so if we're multiplying a rational by an irrational, the answer is going to be irrational. And the sum or product of rational numbers is going to give you a rational answer. So if you add two rationals together, or if you multiply two rationals together, you're going to get a rational answer. So let's take a look specifically at some radical expressions. Remember, radicals those are our square roots. Sometimes square roots are rational, sometimes they're irrational. We learned how to simplify radicals. If you'll remember, we used the analogy of jail, and if you have a buddy that can break you out and bring you out of the big house, then you get to leave the big house or leave underneath the square root. If you are left alone, then you have to stay put. Okay, so we make our prime factorization tree, we make our factor tree. So here we broke it down by 2 and 350. 2 is a prime number, so I can't simplify that any further. I go over to 350, which can be broken down into 2 and 175. 175 can be broken down into 7 and 25. 7 is prime, I can't go any further. But then 25 can be broken down into 5 and 5. It's a perfect square. Okay, so we take our pairs out. Okay, I've got a pair of 2s, they're buddies, they get to come out front. Same with my pair of 5s, they get to come out front. But this 7, he didn't have a buddy, so he's left inside the square root. So 30 square root of 7 is our final answer. And it's 30 because we brought out the 5 and the 2, and 5 times 2 is 10, but we had the 3 to begin with. So you can't forget the guy that's already out front. We multiply all 3 of those numbers together, and that's what gave us that 30. When we add or subtract our radicals or our square roots, the radicand, the part underneath the square root, has to be the same. So right here, these are both square root of 6s, so I can just add the number out front. Add the coefficients together, 7 square root of 6. When you're given an expression like this where they're different, you have to try to simplify all of your square roots first. Once you do that, then you can look to see if you have any radicals or radicands that are the same so that you can simplify. So here we noticed 125 could be broken down into 5 and 25, and then 25 gets broken down into 5 and 5. So I can take out a pair of 5s. That pair came out front, and then I was left with 1 5 who was all alone and left inside. So then I had 7 square root of 5 minus 5 square root of 5. We just simplify those coefficients, and 7 minus 5 is 2. When we multiply, they don't have to look the same. You just multiply the outside pieces, the coefficients, together. So here I just have a 4. I don't have any other coefficients, so it just stays 4. And then we can multiply all of the radicands together, those square root parts. So 2 times 3 times 5 gives me 30. 4 square root 30 would be my simplified answer. Okay, so moving along with some more Unit 1 topics, we have precision and accuracy. So a quantity can be precise or approximate. Okay, so when an approximate quantity is used, it's important that we consider its level of accuracy. So here's some examples over here. So is precision needed? Do we need to be exact? So a dosage of medicine, it is important that we are precise. Okay, we need to have that exactness. When we're talking about the distance from the house to the mall, it's not as important that we are exact. So let's say you live about a mile away from the mall. It's okay if you say about a mile. That person doesn't need to know that it's 1.04 miles actually from your house to your mall. Having that approximation would be okay. So when we talk about things like units, we often get into unit conversion and dimensional analysis, and this is just when we're converting our units. So when converting any type of unit, you want your unwanted units to cancel out. And then your wanted units, you want them to remain. So here, if I want to convert 309 yards to feet, I take my 309 yards and I want to eliminate yards. So I set up my conversion fraction here. I put yards in the denominator because I need those to cancel. Well, since I'm going from yards to feet, I know that there are 3 feet in 1 yard. So I write my fraction, my yards cancel, and then we just multiply straight across. 309 times 3 gives me 927 feet. Okay, then over here, convert 45 miles per hour to feet per minute. So this time we have miles per hour. I have a fraction describing my units here. This is the dimensional analysis part. So I've got miles over hours. I need to convert miles into feet, and I need to convert hours into minutes. So there's kind of 2 parts happening. So if I start with the miles, I know that there are 5,280 feet in a mile. So my miles cross out, they cancel, and I'm left with feet. I don't have to do anything else. With my hours, they were in the denominator, so they need to be in the numerator so that they cancel. And I know that there are 60 minutes in 1 hour. So I've gone from miles to feet, hours to minute, and we just multiply straight across. So 45 times 5,280, we get that answer, and then we divide by 60. My final result is 3,960 feet per minute. Lastly, we have this example here. It's a word problem. When Justin goes to work, he drives at an average speed of 65 miles per hour. It takes about an hour and 30 minutes for Justin to arrive at work. Okay, so here's the average speed. We also know the time. His car travels about 25 miles per gallon of gas, so he gets 25 miles per gallon, and they tell us the cost of a gallon of gas. I want to know how much money he's going to spend on gas. Okay, so if he's going the speed of 65 miles per hour and it takes him an hour and 30 minutes, the rate times the time gives me the distance. So 65 times an hour and a half, or 1.5, that's 97.5 miles to work. Now, if I want to know how many gallons of gas that's going to take, well, he's going a total distance of 97.5. I'm going to divide that by 25 miles per gallon to figure out how many total gallons he is using while driving. So 3.9 gallons is the total amount that he uses to go to work. And it costs $3.65 per gallon. So I'm going to multiply the amount of gas he needs by the cost of the gas. So the total cost one way to get to work is $14.24. All right, some other important vocab from Unit 1, parts of an expression. Remember that a term is separated by a plus or minus sign. So here 3x is one term, the constant 5 is another term. Here you can see there are 3 terms if I'm looking at something like this because it's separated by a minus sign here and a plus sign here. The idea of a factor, what is being multiplied together, okay, those are factors. So here, like the 5 is being multiplied by x cubed, so those are both factors. And then here, the -2 and the x and the y, each of those would be a factor of that term. The coefficient is the number that's in front of a variable. So in this case, it would be the 5, right here the 2 would be a coefficient, over here the 3 would be a coefficient. And a constant, those are terms that contain only numbers. So the 5 is a constant, the -2 is a constant. Over here, this 4 is a constant, this 1 would be a constant, this 5 would be a constant. So that's just some review of those terms, as in vocabulary. So we want to identify the terms, coefficients, and constants of the expression 5x squared minus 3x plus 8. So here is my expression. I want to identify each of these three parts. So the terms, remember, those are separated by the plus or minus. So I have that first term, 5x squared. The middle term is negative 3x, and then my constant term happens to be 8, which I've just identified as the constant. My coefficient, so the numbers outside of the variable, so the 5 and the -3 are my coefficients. You can also find a greatest common factor when given expressions. There isn't always a greatest common factor. Sometimes it might just be one, but a lot of times there are. So you look for a number that you could divide evenly out of each term, and you also look for any variables that you could divide out of each term. So there's kind of two parts there. So if I look here, I have 3, 6, and 15. Well, I know that I can divide 3 out of 3, I can divide 3 out of 6, and I can divide 3 out of 15. So 3 is my numeric part, or the coefficient part for my greatest common factor. And then I look for the most x's that I can take out. So you're actually kind of looking for the smallest x in one of my terms. So here I have one x that I can take out. I can also take out one x from my middle term and one x from that first term. I couldn't take out any more x's because I don't have any more x's to give in this last term. So that's kind of what I'm talking about, where you look for the smallest amount. So my greatest common factor in this case would be 3x. So polynomials, really quick. Polynomials, when we classify them, if they only have one term, they're called a monomial. If there are two terms, they're a binomial. 3 terms, a trinomial. And if you have anything more than 3 terms, we just call it a polynomial. Poly means many. Degree of 1 would be linear. That's something like 2x plus 4. A quadratic, that would be like an x squared term. Cubic, that would be x to the 3rd, and quartic would be x to the 4th. When we're multiplying polynomials, we distribute, or we use the FOIL method, if you remember that. So we just simply multiply, we shoot our rainbows through to all the terms inside of our parentheses. And when we have something that has more than one term, you have to do it twice. So you'd have to shoot your rainbow through for the first term, and then you shoot your rainbow through again for the second term in what's out front. When we're adding, we just combine like terms. So I look for everything that has the same variable part. These are both x squared terms, so I simply just add my coefficients together. So 8 plus 5 gave me 13x squared. We do not change the variables when we are adding or subtracting. You only change your exponent to your variable when you're multiplying. Remember, you add your exponents when you're multiplying. So here you can see we had x squared, or 2x times x squared, that turned into x to the 3rd. And then when we're subtracting, remember we want to change the sign first before we go ahead and add. So this was positive, it becomes negative. This was negative, this was positive, it becomes negative. This was negative, it becomes positive. We change all the signs, and then we just combine like terms. So 11x squared minus 14x squared, that's going to give me that negative 3x squared. Negative 7 minus 2 gives me negative 9. 1 plus 5 gives me 6. And then lastly, we have applications of polynomials. A lot of your application problems with polynomials are going to be kind of geometry examples, talking about area or perimeter. So in this example, it says a rectangle has a length of 3x plus 1 and a width of 2x. Notice we drew an example because that's kind of the easiest way to kind of visualize what's happening. And then it says find the expressions for its perimeter and area, then confirm that each is a polynomial. So remember, perimeter, we add up all 4 sides, and in a rectangle, the opposite sides are the same. So I have 2 2x's, that's why we're adding them twice, and I have 2 3x plus 1's, because It's happening twice. So then we just simply add up all of our like terms. 2x plus 2x plus 3x plus 3x gives me 10x. My constants, 1 plus 1, gave me 2. This is, in fact, a polynomial. Area, we multiply base times height or length times width. So 2x times 3x plus 1. I just shoot my rainbow through, I distribute that 2x, and I end up with 6x squared plus 2x. Lastly, the diagram here shows an unshaded square inside of a shaded square. I know the length of this shaded square is 2x plus 7. The length of my unshaded square is x minus 2. They're squares, so remember that all the sides are the same. So if it asks me for the area of the large square, okay, area of the large square, we're simply just multiplying those two sides together. So 2x plus 7 times 2x plus 7, you're going to distribute or FOIL, multiply that 2x to both terms, and then that's 7. This is that final answer. What is the area of the smaller unshaded square? They did the same thing, but this time they used x minus 2 times x minus 2 because I have the same side. It's a square. Once they multiplied those through using FOIL, you're using that distributive property, we ended up with x squared minus 4x plus 4. And then they ask me for the area of the shaded region. That's what's left over. So we can subtract the big square from the little square, and that's going to give me the region left over. So we take this polynomial and we subtract it from this guy, and we just subtract our like terms. So 4x squared minus x squared gave me 3x squared, because 4 minus 1 is 3. 28 minus negative 4, remember we're subtracting, that's going to turn this into a positive. So 28 plus 4 gives me that 32. This was a positive, so it's going to turn into a minus when we subtract, and 49 minus 4 gives me 45. So that takes a look at a quick summary of what you might see in Unit 1 examples on EOC.